Okay, hello. So this is actually the third video in the series that I'm doing on step maths questions, and I'm just choosing them more or less at random based on what looks interesting, what might be useful for people to see. So this is step paper 3 from 1988. Actually, it's a very old paper, and it's question 11. Actually, in those days, step papers were divided into paper 1 and then further maths paper A and further maths paper B. So this is further maths paper B, it's the last, so it's roughly equivalent to step 3. Now these very old papers, if you get a chance to look at them, you should be careful because some of the topics covered are not anymore included in maths and further maths A level. Certainly I wouldn't really advise students to look at the papers earlier than about 1994. I forget the exact year, but around that year the syllabus changed. So the ones from about 94, 95 onwards are useful, and the ones from about 2000 onwards are the most useful. But anyway, some of the questions in these old papers are very good and very interesting. Now this one is not a particularly difficult question, I think, but it's a good kind of solid practice question for mechanics. So let me note that this is a mechanics question. And I've shown it on the left here. You can take some time now to read it and try to understand it. The background knowledge, you could solve this with just basic mechanics knowledge from A-level maths, as long as you also know about moments. But it's more suitable for students who've studied further maths, because in further mechanics we cover a lot of questions of this type. So please do go ahead and try to solve the question on your own. Okay, so now I'll start showing my answer. So let's go through the question. It's quite a lot of detail here to read. So first of all, the ladder is uniform and it has length L. So here's the ladder, and uniform means that even distribution of weight. So an even distribution of weight means that the weight force can be considered to act through the center of the object. Okay, one end is in contact with a smooth ramp, so mu for the ramp is 0, so the mu up at this point here is 0, that's smooth contact, and the angle is given. The foot of the ladder rests on horizontal ground at a distance L over root 3 from the foot of the ramp. The coefficient of friction between the ladder and the ground is mu, so this is rough contact here, and the coefficient of friction is mu. So the ladder is inclined at angle pi over 6 to the horizontal in the vertical plane containing a line of greatest slope of the ramp. Okay, you should be used to that kind of language. It just means everything is happening in one vertical plane. A labourer, so that's a person, mass m, is going to climb to the top of the ladder. So part 1, we've got to find the value of mu if the ladder slips as soon as the labourer reaches the midpoint. Okay, so what does this statement mean? It means limiting equilibrium when labourer at midpoint. So to find the value of mu, we're going to have to assume that the labourer is standing at the midpoint of the ladder and that this is giving limiting equilibrium. Okay, so let's start drawing some force diagrams for this. In a question like this, it's really important to draw a good diagram, so I'll make this big. Hold on, let me think about the geometry of this. Okay, I'm going to need a fairly big diagram. I'll move this over here somewhere, the middle of the page. Make some more room. Okay. Now I want to start labeling the points so I can easily refer to them. So let's say this is the point where the ladder touches the ramp. Q is the point where the ladder touches the floor. And also, I'll use a different colour for this. We have the ramp itself, or the front of the ramp there. So let's say that the ramp touches the floor at this point. And call that S. Obviously, you can call these whatever you want. And I'll drop a perpendicular from P onto the ground, so a vertical line should be vertical down to the ground here, and we can call this point maybe R. Okay. Now we know some of these angles. Let's first draw the ground. There's the ground. So we know some of these angles. We know that this I'll use red for angles. So this angle is pi over 6 according to the diagram. And what else? So we also know the angle here is pi over 6. Okay, so it's quite a simple geometry. Now we also know some lengths. Let's mark them on. We have the length from S to Q as L over root 3. So L divided by root 3 is the length from Q to S. And the length from P to Q is the length of the ladder, and that's L. Okay, I'll maybe draw some dotted lines there to show that. Okay. Now let's start thinking about forces. I'll draw the forces in maybe some kind of blue colour. So first of all, what forces are acting on the ladder? So I'm going to draw here a free body diagram, FBD, of the ladder. And just in case you don't know what that means, a free body diagram shows all the forces acting on one object and no other forces. So let's consider the contact with the ground. Well, we have, what colour am I using here? We have a force which is a normal contact force, I'll call it N1, exerted by the ground on the ladder. We have a corresponding friction force, which I'll call F, exerted by the ground on the ladder. Notice it's pointing to the left. Why is it pointing to the left? Well, that's because the ladder is tending to slip with Q going to the right, so friction is trying to prevent the ladder from slipping. Now, what other forces do we have? Well, we have a contact force. Now, we should be careful about direction here. A contact force exerted by the ramp on the what am I saying? A contact force exerted by the ramp on the ladder, and that don't want to make this too complicated, but that force has angles such that it is normal to the surface of the ramp PS. So the direction of N2 is perpendicular to that direction PS. Okay. Now, that's not all the forces, is it? We have at least one more force. It's actually two forces together, isn't it? In the middle of the ramp, we have of the ladder rather, we have the ladder's weight, but we also have the labourer. If I just draw him here, we have the labourer and the ladder's weight acting at the same point. Now, they both have mass m, so the total weight is 2 mg there. Okay. So here in blue we have drawn all the forces acting on the ladder. So there's effectively 4 forces, N1, N2, F and 2 mg. So let's see what else we know. Well, we know we have limiting... Sorry, let me take all this to the other side. Over there, there we go. Now we know we have limiting equilibrium. So what does that tell us about these forces? It tells us that F is equal to mu times N1, where mu is the coefficient of friction at Q. Okay, so that's nice. Now we're going to try and find a value. So what the question, this is part 1, isn't it? Part 1, what the question is asking us to do is to find the value of this quantity. So to do that, we'll have to apply some equations based on equilibrium. So what do we have available? We can resolve the forces in particular directions, and we know that the sum of the components of all the forces in one particular direction must be 0, because the resultant force on the ladder is 0 because it's in equilibrium. We also know that the moment, the sum of the moments due to the forces about any particular pivot is also 0 for the same reason, because we have equilibrium. So we're going to have to use equilibrium equations, and this is something you're probably familiar with, in order to find the values of, or let's say the relationship between F and N1, such that we can substitute here and get the value of mu. Okay, as usual with these questions, there's more than one way to do it. I would emphasize that it is certainly possible to find the value of mu by applying Lami's theorem. So you should know that Lami's theorem says that if there are 3 forces acting on a body, which is in both linear and rotational equilibrium, then it's true that the lines of action of those 3 forces pass through a single point, and that the 3 forces taken together form a complete triangle. Now here we have 4 forces, but the way that you would deal with that to use Lami's theorem would be to take F and N1 as a total contact force C, where C is the vector sum of F and N1, and then you would observe that the line of action of C must cross the same crossing point as the crossing point of N2 and 2mg. So the lines of action of these 2 forces cross somewhere up here near the top of the diagram, and C will have to also pass through, the line of action of C will also have to pass through that point. And from doing that you would see the ratio between F and N1, which is mu. Okay, I said that very quickly because I don't intend to do the question that way. That is a perfectly good way to do it, but I won't do it that way. I'm going to use another approach which I like to teach to my students. I think it's definitely a worthwhile idea. And what is that idea? Well, of course we can use moments. If we use, maybe let's ask ourselves a question like, should we use Lami's theorem? Should we use resolving forces vertically, horizontally? Should we use moments? Now, resolving, so I've talked about Lami's theorem, that's a good method. Resolving horizontally and vertically may give us some useful information, but there's a slight problem, which is that we're not really sure how to split this force N2 into vertical and horizontal components. In order to do that, we need, well, that's not exactly true, is it? We can figure out the angle that N2 is with the horizontal, because we know this angle is pi over 6. So this angle is pi over 6, so this angle is pi over 6. So we can split this into 2 components and then write 2 simultaneous equations, one with horizontal equilibrium and one with vertical equilibrium. And certainly that will work. So it's almost like what I'm saying here is, yeah, that method is good, yeah, that method is fine. I'm going to use a moment method because I think it's a little bit more straightforward, and I think the algebra will end up being simpler. Now let's think, if we're going to take moments, the question always becomes, which pivot? Which point should we take as a pivot about which to take moments? So there are several plausible candidates. If we take the point Q, then both N1 and F will have 0 moment. It will be easy to calculate the moment due to 2mg, because the perpendicular distance will, if I just draw a dotted line here. Did I give that point a name? Yes, I'm going to give that point the name T. Yeah. And that point was S there. You know, basically the moment due to 2mg around Q is TQ times 2mg, so that's pretty easy. But it's a little bit more annoying calculating the moment due to N2. It certainly can be done, and that's fine. But I'm going to do it a different way. Let me show you what I mean. First I'm going to take moments about P. And the reason I wanted to start with that is because this will naturally give me... See, the problem is I don't know the value of N2 just yet. So I think taking moments about P is the natural first step, because we don't know N2, and in order to work it out we would have to do a bunch of resolving, and we get simultaneous equations, which I don't want. But if I take moments about P, let me maybe do this lower down. If I take moments about P, then the effect of N2 is 0, so I can just ignore it. Because remember, I'm being guided. I'm starting from this point here, right? So I want equations giving me f and n1. I don't want equations with n2. So moments about P has no effect due to n2. Now let's do some basic geometry to see what happens. The perpendicular distance. Let's just put the distances in as letters here. The clockwise moment due to the weight is 2mg multiplied by the distance rt, because rt is the perpendicular distance from that line to and the other clockwise moment is due to f. That's f times the perpendicular distance pr, that vertical distance. Now the anti-clockwise moment is just n1 multiplied by the distance rq. Now these three lengths are easy to calculate because we know the length of the ladder is L. So let's write that in detail. 2mg. So 2mg times L over 2 times sine pi over 3. You can verify this easily yourself. F times PR, F is L times sine pi over 6, and then RQ is L times cos pi over 6. Yeah, so RQ is just L cos pi over 6. Okay, obviously that simplifies down a lot. We can get rid of L, and we get mg root 3 over 2 plus f over 2 equals n1 root 3 over 2. So we know that f is mu n, so mg root 3 plus mu n1 equals root 3n1. So sorry, we need a formula for mu. Mu is root 3 n1 minus root 3 mg all over n1. So that's root 3 1 minus mg over n1. Let's call that equation 1. Now of course this is not quite enough, because we know that well, because we don't know n1 yet, so we need to find a formula for n1 in terms of the weight mg. So maybe I can annotate that. So we need n1 in terms of mg. Now let's look back at the diagram and ask what's the simplest way to get that information. Well, if I want a relationship between n1 and mg, and I want to do it in just one simple equation using moments, I'm going to have to find a point where the effect of n2 and the effect of f are 0. Now I want to emphasize there isn't only one way to do this. You know, you could take moments about q. I suspect a lot of students would probably do that. But why not just get the answer in one equation by finding that particular point for which the moment of the friction force F and the moment of N2 are both 0. Yeah? So if I draw the line of action of N2, I want a pivot point which is on this line of action, because I want the effect of N2 to be 0. But I also want the effect of F to be 0. So the only possible point which is, in other words, I want the point which is the crossing point of the lines of action of the two forces which I do not want to include in the equation. Having done that, the moment equation I will get for that pivot point will only involve mg and n1. Yeah? mg here and n1 here. So referring to this diagram, I'm going to have to maybe make a copy of this diagram, otherwise this will be impossible. Let's see if I can do this. It's a bit tricky. Okay, I think that worked, yeah. So in order to do this, let's see if it works easily here. Right, let's make a new page. Okay, so I'm going to take U as the pivot. So if we take U as the pivot and take moments, we see that 2mg has a clockwise moment and the perpendicular distance is ut. N1 has an anti-clockwise moment and the distance is uq. Now ut is ur plus RT. Now the easiest way I think to get UR is to observe the angle. So the angle, right, the triangle QSP is isosceles. So SP, right. So basically, the question here is what's going on with. Okay, so that angle is pi over 6. So let's do some angle chasing here. That angle is also pi over 6. Okay, so that angle is pi over 3. Oh, I see. So if this angle is pi over 6, well, what's this angle here? We know that QRP is a right-angled triangle. This angle is pi over 6. Yeah. So this angle must also be pi over 6 to make pi over 3. So that's pi over 6. So we can see, for example, that PS must be the same as SQ, and SQ is already given. SQ is L over root 3. So we know the length PS. So what about the length PR? So PR, if we consider the right triangle SRP, we see that PR is PS cosine pi over 6. So that's root 3 over 2 PS. So that's root 3 over 2 L over root 3. So we get L over 2. So PR is L over 2. Oops. Alright. Now, what about PR is LO, so I need UR, so I need the angle, I think I need the angle QUP, don't I? So QUP is pi over 6. Why is that? Because, okay, that's a right angle. I see. Right, I see. So we can see, for example, again, angle chasing. This is 90 degrees, the angle between the line UP and the line PS is 90 degrees. So the angle here is 90 degrees. So if this is pi over 6, this is pi over 3. If I can just show you with my mouse. So therefore it's obvious that this angle, again we have another right angle triangle, this angle is also pi over 6. So actually, as it turns out, this length UP is L. Maybe that was obvious, but one way or another, either chasing angles or just making some simple observation, you can figure out that angle. Okay, so what we need now is the length UT. Now we're almost there, because we know that RT is L root 3 over 4. Sorry, what am I saying? RT is... okay, let's just do this very carefully. We need to find the length RT. Oh, I see, yeah. So let's consider the length UT as being composed of UR plus RT. Now UR, we can use the triangle UPR. We know this length is L over 2, so tan pi over 6, considering this angle here, must be PR over UR. So UR is PR, which we just calculated as L over 2, divided by tangent pi over 6, and tangent 30 degrees is 1 over root 3. So UR is root 3L over 2. Now RT is actually the distance from this line to the ladder there. So that's L over 2 sine pi over 6. So that's L over 2, which is the length from P to the midpoint. I should call the midpoint M, sorry. So the length PM sine pi over 3 will give me the distance RT. So that's L over 2 sine pi over 3. So here I'm getting L times root 3 over 2. Sorry, what am I? Yeah, I see the mistake I made here. Oops, this should be moved here because we've now moved on to calculate. We've now moved on to calculating. Oops, let's just delete that. So UR was root 3 L over 2, and RT, which I'm calculating now, RT is L root 3 over 4. So root 3 L over 4. So finally UT is UR. So we're going to add UR, which we calculated here, and RT, which we calculated here. So UT is L root 3 over 2 plus root 3 over 4. So that gives me 3 root 3 over 4 L for UT. Now UQ, you can see, is just because this length here we decided was L. So this is an isosceles triangle, so we're just going to write UQ is 2UR, UQ is 2UR, and that would be root 3L. Okay, so finally our moment equation becomes 2mg times ut, which was 3 root 3 over 4l, equals n1 times uq, which is root 3l. So root 3 cancels, l cancels, and 2 cancels with 4 to give 2, so n1 is 3mg over 2. So having found this formula for n1, we can just substitute it back into our previously existing formula here for mu. Mu is root 3, 1 minus mg over n1. So mu is root 3, 1 minus mg over n1. So mu is equal to root 3, 1 minus mg over 3mg over 2. So that's root 3 over 3. And that's the answer to the first part. Okay, I admit it takes a little longer than it maybe is convenient to draw out all this detail on the diagram. So maybe on reflection it probably is better to use, let's say, Lami's theorem. But you know, that's a good exercise for you. I think if you want to be really good at this type of question, it's important to try the questions in different ways to try and get the answer and see which way is more convenient in each case. So I've done the question using pivots. Now if we go back to the question, the second part, similar but a little different. Find the minimum value, so here's the question again, sorry, look at the bottom. Find the minimum value of mu which will ensure that the labourer can reach the top of the ladder. So if the labourer is to, let's look at the diagram here, if the labourer is to continue climbing from this point and go all the way to the top at P, well then his mg, his weight force, will be acting at P, and the minimum value of mu will again correspond to limiting equilibrium. So here the limiting equilibrium is occurring at Q. That's the only place we have a variable friction force. There's no friction at P. So we're basically going to repeat the analysis, but this time with an additional mg force here. Now what I'll do therefore to save some time is make a third copy of this diagram, I think. Hopefully I can get it right. Yeah. I'm going to make a third copy of this diagram, but then edit it slightly so that we can consider the case of the labourer. Consider the case of the labourer being at the top of the ladder. So let me delete my labourer. So that's my labourer gone. And now my labourer is going to be standing at the top of the ladder here, which will make the diagram a bit more messy. Now the weight of the ladder will be reduced at M here to a single mg force, and there'll be an additional mg force pointing downwards here. It's a bit difficult to draw, isn't it? Mg, let's say. Okay. So now we're basically repeating the analysis with this slightly more complicated case. But the good thing is that a lot of the analysis just repeats directly. We've really done all the hard work in part 1. And I think that's not an accident. You know, if you had tried to solve part 1 using Lami's theorem, you would have treated F and N1 here as a single force. You would have treated this as a single force, and then you would have quite easily have figured out the crossing point, done some basic geometry, and found mu. But that way of approaching this question would fail here, because we've got 1, 2, 3, 4, 5 forces. So in order to apply Lami's theorem, we would have to combine both F and N1 and also Mg and N2, and I think it would start to get even more complicated. But the way I approach the first part of the question may look messy, but it has a big advantage in this more general case. Because look, for now, if I take moments about P, I'm going to get almost exactly the same equation as before. let me actually make a copy of my original equation for moments about P. So moments about P, I said as follows. Here it is. Okay, just copy that. And I'll paste it down here. Okay, I'll just remove this. So moments about P, there's no effect due to N2, but in this case there's also no effect due to labourer's weight, right? Because the labourer is at P. So that means that the equation will be exactly right with these three terms, one for the weight at M, one for the friction, one for N1, except the weight at M is now mg and not 2mg. So all I have to do is remove this 2, and then this equation is correct. Now the lengths are the same, so it's just literally a case of removing this 2 here, and then again rearranging this equation. So let me just repeat that rearranging process. What am I doing here? Oh, this is a bit, yeah, okay, so let me write it carefully. Mg over 2, and sine pi over 3 is root 3 over 2, plus f over 2 equals n1 root 3 over 2. So now I've got, remembering that as before, f is mu n1 in limiting equilibrium, so that's because limiting equilibrium. So what does this rearrange to? Multiply everything by I don't know, 2 or 4 or something. Multiply everything by 4. I've got mu 2 mu n1 equals 2n1 minus 2 root 3 n1 minus root 3 mg, that's right. So what's that? Mu is equal to I don't know, root 3 2n1 minus mg over 2n1, or something like root 3 1 minus mg over 2 n1. So we just slightly altered the equation. We probably didn't need to go through this process. It's very obvious. But anyway, we've now got mu is equal to root 3 1 minus mg over 2n1 instead of, well, just this 2 is different. So that part's straightforward. And now also I can repeat the see again, just as in the previous part, again, this is where there's a method in my madness, yeah, because you probably think my method's a bit mad, but the method in my madness is that the whole structure of part 1, it repeats perfectly in part 2. And by the way, this is part 2. Labourer at P, yeah. So the method in my madness now, look at what happens if I take moments about U. Everything that was true before is still true. The line of action of N2 passes through U, the line of action of F passes through U. So I have now 3 terms in my equation, mg, mg and n1. So again, it's a linear equation relating mg and n1. It just has one extra term. So let's use, okay, I need access to the diagram, don't I? So I'll probably just make another copy, best I can. Yep. Oops, gone all the way down there. Okay. So here's the diagram again, and what I'm doing is observing that if I take moments about U, I get the following equation. Clockwise moment starting with the labourer's weight, that's mg times a perpendicular distance UR plus the ladder's weight mg times a perpendicular distance UT equals N1 times a perpendicular distance UQ. Okay, so on the left hand side we have UR and UT, and we already calculated these. UR, let's just find it. Where's UR? So UR is root 3L over 2, and UT, let me use another colour to show this. So UR is this, and UT is this. So root 3 over 2 plus 3 root 3 over 4. So root 3 over 2 plus 3 root 3 over 4 times L is the value of UR plus UT. So this needs to be multiplied by mg, and then N1 as before is multiplied by UQ, which I think we worked out to root 3L, didn't we? UQ was root 3L. Where's UQ gone? UQ, yeah, so UQ was root 3L. So that's root 3L there. So obviously let's cancel our L's and let's simplify this. We have 3/4 plus a half, so that's 5/4 of root 3. So I've got 5/4 cancelling root 3 and L, and I've got mg equals N1. So now we can see that the value of the contact force N1 is larger. It's 5 over 4 mg, and I can simply substitute this value back into this formula for mu, and that will give me the final answer. So the final answer is that in this case the minimum value of mu is root 3 1 minus mg over 2 times 5 mg over 4. So that's 5 mg over 2, so that's 2/5, so that's 3/5, so that's 3 root 3 over 5. So that's the minimum value. It's actually worth noting that the number 3 root 3 is going to be more than 3 times 1.7, which is more than 5.1. So actually this number is bigger than 1. But don't make the mistake of thinking that the values of mu have to be less than 1. That's not actually correct physically. This number is actually a little bigger than 1. So it's saying, you know, that basically the ladder has to be extremely rough for the labourer to be able to stand at the top of the ramp, which is, you know, completely logical, really. Anyway, so that's the end of that question. If there's anything, so what can we learn from this, reflecting on it? Well, the setup. Well, I suppose the first point is that these types of questions are often some of the easiest questions on the exam if you know mechanics reasonably well. I have noticed on occasion that questions of this type, involving simply resolving forces and taking moments, they can sometimes be answered very quickly and simply, as long as you do your modelling correctly. So the stages are: you make a diagram showing the forces on the relevant object or objects, there might be 2, and you make a choice about basically one of these 3 methods or some combination. Yeah. Anyway, so I hope that was useful. I think I'll leave it there. So thanks for watching.